My name is Elijah, and I'm going to be talking about something that I'm really excited about, which is an open source library that we built called Hamilton. Specifically, I'm going to be talking about building scalable and sustainable feature engineering with it. Cool. So what I want you to come home with from this talk. I want to convince you that maintaining feature engineering code can be difficult. Hamilton can help you build sustainable code that sort of lasts longer than the project you're working on, and build scalable code that can scale up with your data. Hamilton can also model your ML workflow end to end. I'm going to talk a little bit about how we do that. And it's easy to get started with and easy to use. Cool. So first about the company that I work at, that I founded. It's called DAGWorks. DAGWorks are making machine learning pipelines easy to manage. Nobody should be afraid to inherit data science code. So just to be clear, I'm not selling you anything in this talk. Everything I'm talking about is open source. But it's maintained and managed by DAGWorks. Cool. So as I said, Hamilton is open source. You can install it in PyPy. You can get started in less than 15 minutes. There's a nice little website to try it out where you can run it interactively in the browser. And we've got all sorts of good documentation that we've worked on. So if you go to tryhamilton.dev, you can go after the talk. There's a nice little way to play around with it using Pyodide. It's some pretty cool technology. All right, so on the agenda today. First, I want to tell you a motivating story of data science pain from my last job. Then, I'm going to talk about the solution we came up with, which is a library called Hamilton. Then I want to talk about how Hamilton can be used to build out feature engineering pipelines, both to make them sustainable, so that you can easily build code that lasts sort of longer than your project and longer than what you're working on right now, and scalable, so that you can build code that works as you get more and more data. Then I'm going to take a step back, look at Hamilton for end-to-end machine learning workflows, and finally, talk a little bit about the open source progress we've had so far and next steps. So let's dig in. All right. So let's talk about a problem from my last job. I used to work at Stitch Fix, where I led the machine learning platform. And one of the first problems that we dealt with was building tooling that forecasted the business. So we needed to know what demand would be like, what signups would be like, what churn would be like, so we could know how many warehouse staffers to hire, how much stuff to buy, how much to send to customers. And that looked like a pretty standard time series forecasting task, right? So you've got data coming in from the business. This is all coming in from sort of like your data warehouse from external sources. Then some process that turns that into a featureized data frame. Then you use those features to build out time series models. Use those time series models to run a simulation and predict the future. And finally, you get a data frame with a forecast. You pass that off to the next team that makes a decision with it, right? So we actually modeled all of this using Hamilton. But I'm going to talk about how we did the featureized data frame piece. So what this looked like initially was thousands of operations on a monolithic central data frame. There's a lot of configuration buried within business logic. So there were a lot of different ways they wanted to generate this data, the different data products that were all sort of buried within if-else statements. There were multiple layers of scripts to execute, store, and visualize this data. And they had a world-class team of data scientists, each with like PhDs in time series forecasting and analysis, that were managing this. So the modeling was great. They had some really sophisticated, interesting stuff, and were amazing at sort of communicating this to the business. But the problem was the code. They kind of ended up tripping over the code. So what got them to this point wasn't going to get them to the next point. And that's where we came in. So what were the problems with this? Well, unit testing was difficult. It was a bunch of sort of procedural manipulations on pandas data frames. So you couldn't just test one piece. You had to run the whole thing. Documentation was unnatural and unenforced. There were a bunch of code comments. You could sort of grep the code, read it, figure out how it should work. It wasn't particularly modular. Sure, you had some grouping into files, but there was nothing guaranteeing that logic that was similar to other logic was placed near it. To think about it as a data catalog, there's just a lot of grepping the code, right? You generated one big data frame at the end, and you had no idea what to do when you wanted to figure out exactly how something was generated or how up to date it was. To debug, you had to run the whole pipeline. There was no just running one piece, and it was slow and complicated. And for data validation, again, you had to run the whole pipeline. This was not really done in reality. So they had the perfect modeling solution to a forecasting problem, and as time went on, this just turned into spaghetti code. So what happens when you have all of these problems and you want to expand your models to new regions? You have to add complex scenarios on management's whim. They were always like, oh, what if we up the marketing spend? How will that impact demand, et cetera? And you have a data bug and very little time to solve it. Well, the answer was this wasn't actually fun. This was a pretty awful time for them. And this was the thing that was slowing them down in their job and not letting them meet the demands of the business. And I want to say this isn't a unique experience to my prior role, to time series forecasting, or even to pandas. This is a pretty general thing. So to date myself with a meme, I don't always write complex data pipelines, but when I do, it's an unintelligible mess of spaghetti code. I don't know if people like this meme anymore, but I'll never get bored of this guy. So that's the problem. What is the solution we came up with? It's this open source library that I'm talking about. And it came from one quick realization, one sort of thought that forms the basis of everything. So the idea is, what if every column corresponded to exactly one Python function? Right? We had a million different columns in this data frame. What if you just wrote one Python function for column? And next, what if the way that function was written told you everything that you needed to know about it? Right? So no moving around to configuration, no sort of jumping around to the code base to other places, no trying to figure out how it's run. Just read that function and tell you what you need to know about that column. And this is basically all there is to it. In Hamilton, the artifact, that column, is determined by the name of the function. The dependencies are determined by its parameters, right? So what does this look like? Well, it's a pretty straightforward approach. If you've ever seen PyTest fixtures, this will look really familiar. So instead of writing procedural code that looks like that, right, you've got the manipulations on sort of a central data frame. You declare it as functions, right? So you've got, here we got dfc equals dfa plus dfb, dfd equals transform of dfc. Instead, you're defining C, so you define the column C to be A plus B, and define D to be some transform on top of C. And just to be clear, Hamilton supports all Python objects, not just data frames and series, but data frames and series are a really natural application, and we have a little bit of syntactic sugar for them. So, just to be clear, the outputs are the function names. These are things you can get later. And the inputs are the function arguments. These either correspond to other outputs or to some sort of input data later. All right, so what does this look like? Well, we've got our functions. Then we've got our, we need to actually run them. So we've got functions and then something called a driver that tells you how to run them, right? And all you do is import your module that defines the functions, instantiate your driver, pass it some configuration as you need, execute it, tell it exactly which functions you want to compute, and you're good to go. Cool. So summing it all up, for each transform, you write a function. Functions declare a DAG. If you don't know what a DAG is, we named a company after it because we're kind of nerdy, but a DAG is a directed acyclic graph. It's really just a way of saying run this before this, run this before this, join these two, etc. So these functions make a DAG just by sort of wiring it together. And Hamilton handles DAG execution, right? So you can say, oh, I want to inject these inputs in and execute these ones. Cool. So you might be wondering, doesn't Hamilton make your code more verbose, right? Instead of writing a bunch of sort of monolithic operations on a data frame, you write functions, and it's like functions are going to be probably 3 lines. There's your definition, your documentation, and your function body. And I want to argue that verbosity is a tool. It's not necessarily a bad thing to be verbose. It's just a sort of tool that you can wield. Verbosity can make it less readable, but it can also make it more readable. And in Hamilton's case, we found that it often makes it more readable because it encodes a lot about the function. But when you do find yourself repeating stuff a lot, we have these decorators that add all sorts of syntactic sugar to it to make it both readable and concise, right? So you can attach metadata to your functions with tag. You can parameterize them, run a function with a bunch of different input values. If your function outputs a data frame, you can have one sort of output per each column. You can add runtime data quality checks. I'll go into that later. You can do configuration-driven pipelines. So say in this condition, this function does one thing, in this condition, this function does another thing. And you can even do something where you run a whole subset of the DAG as its own function, right? So there's a pretty powerful language here that's meant to make it a little more concise if you need to. All right, so to summarize, Hamilton is a new paradigm. It forces you to write transforms in Python functions. These Python functions provide everything you need. Unit testing is simple. They're plain old Python functions. For documentation, you just have the doc string. It's easy enough. They're nice and modular. They're broken into small pieces, and then the functions are organized into files. So it's easy to sort of like co-locate similar logic. Hamilton naturally forms a data catalog in that it doesn't actually store the data, but the code from the sort of central feature definition store, right? So if you want to know how your data is generated, you can look in there and get everything you need to just by grepping the code base and looking for a def function name. Debugging, you execute functions individually, and you can put in breakpoints. You can say like, oh, why does this piece of data look weird? You can sort of walk back through the DAG pretty easily. And Hamilton makes it easy to get trustworthy data. So data validation is included out of the box. These decorators form powerful higher order operations, and the driver allows you to decouple the transform definitions from the execution. Cool. So this initial use case has been running in production now for actually close to 4 years. It manages, when I last checked, 4,000 plus feature definitions. I'm no longer at Stitch Fix, so I think it's probably grown to 5,000 or 6,000. Data science teams love it. It enables the thing they did all the time, this sort of monthly process of model and feature update to be 4 times as fast. It's easy for them to onboard new team members because the code is self-documenting and pretty trivial to understand the structure. Code reviews are simple. It's just you're looking to see how the lines of code have changed, and you can sort of isolate the diffs to a function. We finally have unit tests, which they never had before. It's fewer bugs and quicker resolutions, so it's easier to, so they've managed to debug quicker, thus ending up with fewer bugs, and the models and features are better because they've had more time to work on it, right? Because they're tripping over their code less. Cool. So this is just some eye candy. The left side is just the commit history showing that data scientists really sort of started taking this over and making it their own. We helped with the initial migration, but they've jumped on it. And then the right side, the airplane, is just a pretty DAG visualization to show sort of how complicated their use is. I think each one of these is like a clustered set of features. This is not important, though. You don't have to memorize it. So, all right, so let's talk about how Hamilton can be applied for more sort of general feature engineering, not just time series. So looking at the ML pipeline, we're going to talk about the rest of this later. I want to dig in to the featureization side, right? Oh, the inference got moved around. So if you look at, like what's a pretty standard, like 10,000-foot view of a machine learning pipeline, you load your data, you transform it into features, you fit your models, and you use your models. Let's dig into the featureization side. Again, some notes. It only works for it works for any Python object types, not just data frames. And it's embeddable anywhere Python runs. Orchestration systems, Airflow, Kubeflow, Metaflow, FlightKit, Prefect, Dagster, et cetera, web services. Hamilton is kind of a Swiss Army knife. It can model your whole workflow end to end. It can also model one little piece. That's how a lot of people get started with it. Cool. So modeling feature engineering. The code, what code needs to be written? Well, you've got to write your functions to load your data, your transform and your feature functions, and then the driver to materialize your data. So this is really just an ETL, right? Extract your data, transform it into features, and then load it into the driver, and execute only what's needed. Right? So load your data from wherever, transform and your data into features, and run your driver to materialize the data, executing only what is needed. Simple enough. What are the challenges with this? Well, again, breaking it into sustainability and scalability, right? So Hamilton is meant to solve the sustainability problem, right? Hamilton helps you solve the problem of highly coupled code, of difficulty debugging and understanding data flows, of messy collaboration on complex pipelines, and of validating your data. And Hamilton has integrations for scaling your data. We didn't want to reinvent the wheel. Not everybody actually has data scaling challenges, but if you do, Hamilton can work with a variety of frameworks. Your data is too big to fit in memory or you can't easily parallelize computation, Hamilton can help you there and make it so that the code to do this is as separate as possible from the code to actually transform your data. Cool. So let's talk about sustainable feature management. How does Hamilton help you decouple code? Well, Hamilton helps you decouple code from your infrastructure and potentially from itself, right? So because your driver handles execution and your functions handle the business logic, the code is naturally decoupled, right? The piece that runs it is different than the piece that defines it. And those are sort of the two pieces. And Hamilton also helps you decouple code from itself, right? So code is organized into functions. Those are natural building blocks. The functions are organized into modules. Those are sort of natural ways to group your functions. And the functions don't actually know or care about Hamilton. They're just reusable Python functions. In fact, if you write everything in Hamilton and you decide you don't like it, you can just take your functions and use them in some other way, right? You have these nice sort of reusable pieces. And the cool thing is if you have all these functions, you can reuse them in different ways in different drivers, right? So if you have different configurations that form different DAG shapes, or you want to load your data from different places, it's just a matter of swapping out one of these function sets or swapping out one of these functions. So naturally modular, naturally decoupled. All right, Hamilton makes it easier to debug your data flows. So if you're trying to knock bugs out, you can just rerun just the broken paths, right? Just say like, okay, I want to rerun this thing, ask for this piece of data, and you're good to go. Python functions make for natural unit tests and natural debugging. Hamilton comes with runtime data quality checks, so it's easy to figure out and sort of detect bugs when they happen, ideally before. And then Hamilton allows you to quickly narrow the search space of data bugs, right? So you can do sort of a bisector search through your DAG to figure out exactly when data looked weird. And the data looks weird problem is one of the ones I've seen most in my career. Hamilton sort of makes it very natural to figure out exactly when that starts. Cool, so Hamilton also makes it easy for you to understand and visualize. There's a whole visualizing the data flow and execution path, and it makes it easy to clearly track dependencies by reading the parameters by looking at this visualization of a DAG. We have all sorts of tooling around this. So Hamilton also makes it easy for you to collaborate with a team. So as it forms a centralized feature definition store, it forces alignment on naming, right? You're actually using the name of everything twice. Once when you define it and once when you refer to it. So the more you sort of use that name, the more you think about it, is the more it has to make sense. These function names actually do something interesting. They turn into nouns and not verbs where they describe exactly what this data is. So you have sort of a nice natural naming where you can say, okay, here's what the data is and here's how it's used, right? Documentation is included in natural and it's all the Python doc string of the functions. And Hamilton helps you minimize conflicts when collaborating because it's all sort of broken into functions and modules, right? It's not just working on one giant monolithic or a few giant monolithic files. All right, and then change management becomes easier with Hamilton. You can store your feature versions in Git. All the changes are in Git history, and the PRs are pretty easy to read, as I mentioned. You can trace the changes back to functions. Here's an example from my previous role. All right, so Hamilton can also help you. So one of the things that's really exciting about making it easier to manage data flows is Hamilton can help you handle data validation. So a question, how can you build a reliable pipeline if your data is bad? The answer is you can't, garbage in, garbage out. But Hamilton makes it easier because it gives you runtime data validation checks, right? So you can see this case, in this case, we're just decorating a piece of data with check output. We want to pass in we're telling it, oh, the data type has to be a float. It's in this range. No nans are allowed, and the importance is warned. So you don't want to fail here. You just want to log a warning. It's a configurable action. Should be pretty easy to read, and now you've got sort of nice data quality integrated in with your data flow. We've got all sorts of basic checks. A few custom built ones for a quick start, so you can check if your data is in range, check if something's nan, check if it's set full of valid categories, check if there are any null outputs, etc. It works with pandas and primitives, but it's highly pluggable. You can kind of build anything you want. And there's more. We have a whole Pandera integration, so if you want to pass in a Pandera schema and check your data frame or your series, it's easy to do. And it's highly extensible. So you can implement the base class to write your own. This is part of the API. You can have this custom check output. And the goal is to add integrations for any type of data frame and data type, and potentially multiple validation frameworks. So great expectations, DQ, Y-logs. No reason we couldn't easily integrate this in. This is a nice sort of clean API. It's meant to be readable. My favorite dummy example is an all prime validator. That's the one I've been using in documentation. But the point is, you can write whatever you want, right? You can access all of this data afterwards to see how your data flow ran and report on that. So to sum up sustainability with some code, the goal is that this should be easy for anybody to read. I mean, Python kind of makes code read like English. This makes Python read like English, especially for the more complicated data stuff. So roughly translated, this looks something like this. The feature client height normalized is owned by the client recommendations team, contains no personal identifying information, is of type float, depends on two upstream features, height zero mean and height standard deviation, has no NaN values and produces values between -5 and 5. Version control shows its changes over time, and you can grep the code base for downstream dependencies. So it's quite a mouthful, but if you feed it to ChatGPT, it'll tell you exactly the same thing. And I figure if ChatGPT can understand my code, then I don't know, I think I can too. So, I don't know. I think ChatGPT can probably understand a lot more than I can. But if it can explain it to me exactly as how I intended it, like it does here, then I'm pretty happy with it, right? So it's a litmus test of sorts. I think we haven't decided whether, as an industry, we haven't decided whether it means anything or not. Cool. All right, so let's talk a little bit about now. We've talked about how you can scale up your team, make it easier to collaborate. Let's talk about how you can build out scalable data with Hamilton, or scalable data pipelines with Hamilton. Cool. So the approach here is to delegate to other frameworks, and Hamilton has a bunch of integrations. Say you want to run in parallel, scale from a single machine to multiprocessing up to a cluster. That's where Ray and Dask might come in. Obviously, they have sort of data set level stuff as well, but we integrated with the parallelism features. And if you want to run, scale your data set horizontally, we have an integration with Pandas on Spark, and also Modin works pretty nicely too for this. And these are just the sort of like natural built integrations. Again, you can use Hamilton with any objects you want, so you can scale up in any way you want. But the goal is here that switching should only require making a driver-side change. So Pandas on Spark requires, is the one caveat. We actually change the data we load in because it's a different sort of data loader framework. Or it's like a different way of sort of loading it. You want a different type of data frame. But that's just one swap out I'll show you in just a second. So how does this look like on Ray? Well, here's sort of a little more advanced version of the example we saw earlier. You import all your features. You create a configuration. You create a driver. Those driver takes in all the feature modules. You say which features you want, and then you execute them, right? Save it. Again, this is actually just an ETL, right? Extract and transform as part of the driver, and then load is that save function. With Ray, you have to add just a few little pieces. So we have this notion of a graph adapter that says, here's how you walk the DAG. And in this case, the graph adapter delegates to Ray to say, like, oh, now execute it in a distributed fashion, right? So we initialize Ray, create the graph adapter, pass it into the driver along with our modules, and then shut it down at the end because you want to give your resources back to your friends. And it's pretty easy. These are the only 3 changes you get to now run your whole data flow in parallel. Same with Dask, right? We instantiate a Dask graph adapter, pass it the resources it needs, pass it into the driver, and shut it down at the end. Cool. And what this does is gets it so you can run using Dask parallelization. All right, and then scaling with Pandas on Spark, it's a little trickier, as I said, because we have to, I mean, Spark is always going to be a little trickier than a few of the other frameworks, but we have to load up our data using a Spark data frame because those get passed through the rest of the data flow. We also pass a spine in because Spark doesn't know about spines, so there's an abstraction there to handle that, spine being the common index with which you join. But then it's the same thing. You use pretty much all the same code, just switch out the data loaders for the Spark data loaders, pass in your features, execute it, and now you've got scaling up with Spark. Cool. So how does this actually work under the hood? Well, you've got your functions and your driver, as we saw earlier. That forms a DAG. We say which ones we want to execute. And then we delegate to ray or Dask, right? By just calling ray.remote or dask.delayed under the hood when we call the function. It's just a simple graph walk. It's pretty easy. And we have an abstraction there to make it easy to walk the graph in sort of any way we need. And with Spark, same deal. Again, we have to load it up in a slightly different way for pandas on Spark. But otherwise, it's pretty easy, right? So we change it to load the Spark pandas equivalent objects instead, and Spark will take care of the rest. Cool. So some caveats before I claim this solves every problem. We use the serialization methodology of the delegated framework. So if you have something constant, you'll have to kind of like figure a way to stick that in. Defaults for memory should work, but fine-tuning at a function level is not yet supported. This is in the Spark case. Python dependencies, you need to manage them. I don't think we want to be in the business of managing Python dependencies. And we're looking to graduate these APIs from experimental status. So contributions are wanted here to extend support in Hamilton. We would love your thoughts. Right now it's under the experimental package, but we have quite a few people using these in production. All right, so let's take a step back. We talked about Hamilton for feature engineering, and let's take a step back. And since the theme of this is end-to-end, I want to talk about how you can model your end-to-end workflow with Hamilton. But it's your choice how much you want to, whether you want to model just feature engineering, just one little piece, or the whole thing. We've seen people do anything across the gamut. Okay, so what does an ML pipeline look like? Well, it's kind of just a fancy ETL. We talked about loading data from a feature store and transforming features in the previous section. And there's a few more pieces, right? You want to train your model. You want to run model inference. You want to evaluate your model's performance. These are all transforms, right? You're taking data and turning it into some other data. And then you want to load, right? So you want to save your metrics. You want to save your artifacts, save your training data. This is all useful for later for building out artifacts that you might need. So for training, for the transform part, you express it as everything as functions, and that's sort of very natural in Hamilton. And for the load part, it's fully decoupled from the logic, right? So what are the values of getting a thing? What can you do by decoupling it from the logic, right? You've got, your function that creates your model, your function that creates your metrics, your function that creates all your features, right? Or creates a few of your features, you can join them. And then you can swap out the model store if you want. If you want to save it on S3, if you want to save it to disk, if you want to email somebody your model, those are all possible just by sort of like swapping it out and using different drivers. The functions themselves are fully reusable in any context. You can swap out the feature source and the feature store, right? So load data up from anywhere, save data to anywhere. And one of the really cool things is you can execute the same code online and offline. So one of the things Hamilton makes it easy to do is say, in this context, I want to run this, and in this context, I want to run this, right? And in online and offline, you're probably going to be running mostly the same code, right? Some people have a issue with like taking pandas series or taking bulky objects and running them in production. I found that that's never a problem, actually. You can run pandas series of ones for map operations, and it's pretty clean and pretty fast. You'll get like, the overhead is almost nothing. And using that, if you have your pandas objects or your polars objects or whatever transforming it, you can just run those in production. And 95% of the code is probably these map operations, right? So that's how you can get the bulk of your feature transformations into production. But there are two other types that you might have trouble with. So if you're doing a join, that's equivalent to a data load in production, right? You say, I want to join my data with this other data source. That's a query out to a feature store. And you can swap out the implementation of that function, right? Say like, okay, in training, I want to join this data set, and in production, I want to load from this source, right? And then aggregation is the other one. That doesn't make sense in it semi-makes sense in a streaming setting. It barely makes sense in a online setting. And you can just, again, swap out the implementation, right? So either your model will hard code the aggregated value, or your data, or you will load your data in from an external source that's been saved somewhere else. So the point is, Hamilton is not a language that will make it so your online and offline will be exactly the same code, but it'll get you close enough that you get by without the vast majority of the pain. So Hamilton can also help you gain visibility onto your end-to-end ML pipelines. sort of lineage is a natural way to, Hamilton naturally gives you lineage, so you can trace the function parameters for managing dependencies, trace the data from source to transforms all the way over to your sinks, to your models, and tag metadata to understand properties of dependencies. So one of the things I've seen people doing is tag different nodes saying these columns or these sort of functions contain personal identifying information, and then tag another node later on saying this contains like an anonymizer, right? So you can get a sense of how data is flowing through, knowing exactly how your GDPR concerns might matter and might impact you. And then Hamilton naturally forms a catalog for your features. It's not a data catalog, as Hamilton doesn't actually care how you store the data, but it is sort of a single source of truth, as in all the data flows through your code, and your code is the thing that's executed. So if you look at how your code is, you should be able to see what data you're storing and how it's getting manipulated. So yeah, so browsing your features is as simple as browsing through code, and then you have your feature names, and you can look that up in your data store or wherever later. And the documentation is attached to the artifact name, so it's pretty easy to figure out exactly what something is, how the code is, and what the data will look like. Here's just a little example of like an internal prototype we're working on that shows sort of like how data flows through the Hamilton system. I think in this case, green is the current set of nodes we're looking at. Blue is, like light blue is data flowing where it's flowing to, and then red is where it's flowing from. And a pretty bold vision for what Hamilton should look like with end-to-end machine learning pipelines. We want it to be the unifying layer for machine learning ETLs. So we found that Hamilton is just a really natural way of expressing the way your data flows through that allows you to sort of bring your own Python frameworks and focus just on the little bit that you're working on at the same time, or the little bit that you're working on when you're working on it. And then, as an API for doing that, there's a lot of possibilities, right? We could compile it to an orchestration framework. Say generate Dagster, Prefect, Airflow, Metaflow code out of Hamilton, and even switch between them if you want, right? You're writing in one API that's clean and readable, and then you can project it down to an orchestration space, effectively giving you the orchestration for free and not requiring you to think about it, right? That's the way sort of the decoupling of concerns. We want to make it really easy to integrate with data quality vendors and open source options. If you've ever saved your data to Arise, to sort of compare online and offline. Uptrain is a new one, fellow YC company. Ylogs is an awesome provider that you can sort of log data to and see how it changes over time. Using data sketches, it should be as simple as pressing a button or swapping out where your data gets stored to, right? And then we want to make it really easy to load from and to a variety of sources and destinations. So you want to load your data from Snowflake, save your data to Snowflake, load your data from DuckDB, transform it in DuckDB, save it to DuckDB. That should all be possible with some simple swaps, some simple sort of like function decorators. And we also want to build out SQL support for a full ETL, right? So Hamilton isn't going to replace dbt. It solves a very different problem. But if your pipeline is just load up a few data frames, join them, and then run a bunch of processing on them, that's where Hamilton excels, and no reason you should have to do sort of like complicated SQL stuff. Cool. So talked a bunch about Hamilton, about how Hamilton works with feature engineering, and about sort of modeling end-to-end workflows and where it's going. Let's talk a little about the open source progress and where we're going next with that. All right. So Hamilton is in early stages, but it's a thriving community. We have some really exciting users, some names these are just a few names that people we talk to on the regular who are making heavy use of it. Growing set of core contributors, and now a full company dedicated to building it. We're looking for contributors, bug hunters, user feedback, etc. We would love your opinions on where we should go next. Things we're working on now. More expressive APIs, so schema for artifact metadata. This is specifying like all those tags and all those metadata. We ideally want a schema. There's a company that wants to has governance concerns and wants to be able to express that using these tags. Adapters for SQL, as I mentioned, making it really easy to load data up from any sort of SQL source and stick it into your data frame. And your idea here, we're actively accepting contributions. I want to make execution more powerful, so do that whole sort of notion of compiling down to data flows, right, to different orchestrations, writing in Hamilton and running in other frameworks. We're building out streaming and generator support. So if you want to do like mini batch training, as part of your function. The Hamilton framework could actually know about that. And then first-class PySpark integration. We have integration with pandas on Spark. We have some integration with PySpark, but we were looking to improve that out. And again, your idea here, would love your thoughts. So give Hamilton a try. We'd love your feedback. Give us a star on GitHub. Create and vote on issues. Join us on Slack. We have a nice community where you can ask questions. We're pretty quick about getting back to you. And yeah, you go to tryhamilton.dev. It's a nice way to get started. And thank you so much. If you have questions, you can yell at me online on Twitter, connect with me on LinkedIn, code with me on GitHub, my email sparingly, and also I'll be answering questions in office hours right afterwards. So thank you so much, folks. Really appreciate the time.